Okay, so I'm looking at, as it says up here, investigation 7, number 6. This is F equals MA at an angle. And sliding down, this box going to slide down the ramp. And the question is, how much time does Patches have to get out of the way? Here's Patches. Okay, a purple cat here. Fill that in. There we go. So there's Patches. All right, so we have to the first thing we're going to do is draw a free body diagram of your box that's going to slide, and given the information here, we know the box it's a 17.5 kilogram box. It's just shown right there. It's going to slide 3.25. Okay, and what we don't know on the drawing is it's a rough surface, and this is 12.2. It's 12.2 newtons of friction. And remember that kinetic friction is always going to oppose motion. If you ever have kinetic friction in the direction of motion, you made a mistake. So let's go ahead and start off the center of this box. We'll do this in blue, I guess. Center of this box. And put that down. So there's my MG. I'm going to make that long enough so that I can work with it and see my angles. I'll leave it in symbols, and I'll also put in what I know, 17.5 kilograms. So 17.5 kilograms. Really, your drawing is your thesis statement. We know the G is 9.81 meters per second squared. Okay, so we also know there's of course going to be a normal force, and normal, remember that normal means perpendicular to the contact surface. Normal is an old term meaning perpendicular. So it's perpendicular to the contact surface. It's a contact force. Whenever I ask you for a contact force, I'm asking you for the normal force. When normal force goes to 0, no more contact. That's how you know it's left the surface. And sometimes you work physics problems that way. All right, so the normal force here is not going to be the same as the weight, because anytime something gets on an incline, the normal force decreases because you're diluting gravity. And so normal force here is going to be, I'm going to try and make it about the right length. Okay, it's going to be 60 on the third. It's pretty long. Normal force is not going to come into play in the actual equation, but it will when we bring in friction later on. The amount of contact will be important. Right now we're just going to deal with a tilted x-axis, and we'll talk about that in a second. The only other force you have back, if this guy is 17, this guy's around 170 newtons. And so you kind of get a feeling that that force back up, which is only 12.2 newtons, just a little bit, it should be a tiny arrow. So not a, if you give me that, I'm not going to count off, but that really is too long. That looks like, if that's 170 newtons, if you multiply those two together, that looks like about 120 or so. It's only 12. And so you want to be careful. I know I'm being picky, but this is where your misconceptions start. If you just start slopping on arrows, you're not going to realize the importance of these forces. So this is about, that's probably still too long, but I've got to show you something. So that's 12.2 newtons, and that's my, I got to label it as well, that's my kinetic force of friction. Okay, so it's instead of static, if this box was sitting there and not sliding, that'd be static. But once it starts to slide, that's called sliding friction, shearing friction, or sometimes called kinetic friction. And the question is, we're trying to find out how much time T equals question mark. How much time will it take? And I want to do that in a different color than my blue, because my blue is my, or what I've picked my color as my forces. All right, so first thing I want to do is tilt my axis. I'll leave that in red. And normally your X, you know how your XY axis is, but now we can't do that because, well, we can. It just makes it easier if we tilt it, and physicists are always trying to make their life easier. So there's my X, and there's my Y. So that's my Y axis, and there's my X axis. And if I do that, it reduces the number of angles I have to deal with. If I leave it as, if I keep this as my Y axis, now I have two angles to deal with. But if I move this as my X axis and this is my Y axis, Now I only have one angle to deal with. Okay. Now it seems like if this guy is almost 107, let's go ahead and multiply it out just to find out what that is so I can tell you exactly. And I see, there it is, my calculator. So I'm looking at a 17.5, whoops, 17.5 times 9.81, and we're looking at 172, we'll say. That's 107, blue, that is 172 newtons, okay? So now I can go ahead and find normal force if you want, but you know, it doesn't do any good. So I'm not into wasting time. Now in packet 5, we'll go back and start to look at that normal force carefully. All right, so if I have 172 newtons versus 12.2 newtons, that's going to wipe it out. But as Galileo said, when I put something on an inclined plane, I dilute gravity. Well, that means you dilute the weight. And so the weight is not really down the incline. Sometimes you refer to it as down the incline weight. Is not, or incline weight, is not 172 newtons anymore. Because it's only, you only get a fraction of that. And so let's go ahead and draw, remember that every vector is the hypotenuse of a right triangle. So let's go ahead and draw a right triangle that goes with this dot, 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 dot. Okay, there's my right triangle. And I'll highlight that. We already got a lot of colors up there. But let me highlight that in, I guess, purple. Here's the right triangle I'm talking about. It's one of the hardest things for students to understand when it comes to inclined planes, is how it affects their forces. So I have this back up the incline. I get a portion of this, which is only 172 times, you know, let's figure it out. If this angle is 25 as it's written, then this really forms a right triangle. There are all kinds of triangles here. You're just going to have to pause me, stop, think about it, and then go back. People are having questions about this, saying, you know, the help videos don't help that much. It's because all you're doing is watching. If all you're doing is sitting there right now watching this, you're probably starting to fall asleep. So you want to make sure that you've tried the problem and you're verifying that you're doing it right, or you're just, you know, you at least tried it. And you realize you're at an impasse, and that's why you go to the video. Or maybe you're just reviewing. But fast forward to where you see, I'll try and keep showing you the picture, but fast forward to where you start to have a question. Okay, but be active. Actively watch me. 25 degrees there. That angle right, that's a right triangle, so that angle right there is complementary to 25 because the three angles of a triangle add up to 180. So that's 90, that's 25. This must be 65? Yeah, 65 degrees. Because 65 plus 25 is 90. Yeah. So that's 65 there. What makes that 65 right here, that is 65 degrees. That angle. So in general, this angle up here will always be 90 minus theta I. Whereas this angle is theta I. In a previous help video, we talked about this. Theta I meaning that is the angle of incline. So in this case, the angle of incline is 25 degrees. 90 minus theta I is 65
please excuse this interruption. Can I please have the members of the softball,
we'll ignore that
tennis,
interruption.
Track, golf, baseball, and soccer team to the floor of the North Gym, please?
All right,
yes,
so
softball, tennis, track, golf,
degrees.
baseball, and soccer team to the floor of the North Gym.
So all I want is this little component of that triangle. That's all I get. I get that really diluted. And I don't get all 172 newtons. If I were to stand on that inclined plane, you wouldn't get all 190 pounds. You'd only get a portion of it. So you're going to get a portion. It's one, so it's going to end up being cosine of 65 because that's the adjacent side. Remember your trig. I'm not asking you to remember all your trig, just the right triangle stuff. That's what will help you in the ACT. That's what will help you in here. So there's my hypotenuse. That is what I want right there. That little piece of the triangle. If that doesn't make sense, Keep watching this again and again and again until it does, because it's going to haunt you from now until May. All right, so 172 times cosine 65. So now let's go ahead and do our summation of forces, and it's in our tilted axis. So summation of forces, I'll leave it in blue, I guess. Summation of forces in the x direction, the tilted x direction, equals MAX. Remember, the first thing we do is a free body diagram. The next thing we do is we go to F equals MA. We've done that, I don't know, what, 20 times now? So you should have it down. Unless all you do is watch and you kind of half listen. Then you don't have it down. But you've got to practice this stuff. So, let's go ahead and show our forces. That's going to be, I'll keep it in symbols first. That is the mg, which is what 172 is, times cosine 90 minus theta I. Alright? Minus this force of kinetic friction, that little tiny 12.2 up there, equals my mass times my acceleration of the x. Once I find my acceleration of the x, I'll go to orange mirror to solve the kinematics of it. And orange mirror just means kinematics. It means not free fall, but every other kind of kinematic. Okay, so now it's time. I could go ahead and solve for a sub x, bring the m over. I'm just going to go ahead right now at this point and plug in. So we have 172 newtons, 172 times cosine of, as I said up there, 65. And that's newtons, minus, as given, 12.2 newtons, equals my mass. Now my mass is not 172 newtons. I've got to do the little magic triangle to remind you. And I know this seems like a crutch to some physics teachers, but I think you need it, many of you. This is weight, this is mass, this is gravity. If I want to know what the mass is, all I got to do is cover it up, and that's weight divided by gravity. So I have 170, go ahead and use the crutch until you get it figured out. 172 newtons divided by 9.81. It would be 32.2 if we were English units, but it's metric, as most of our problems are, times my A sub x. Okay, now I punched that into my calculator, and I really wish I had it already all figured out, so I don't just sit there and watch me punch my calculator. I'm going to do that. Okay, I'm back. I have my Martha Stewart key here, so I've already got, and this, by the way, is on the internet. It's on my website, the key to this. So I end up with acceleration, stick it back up here, acceleration equals to 3.45 meters per second squared. That's pretty fast. Considering if I just dropped it free fall, it would be 9.81. So we're going about 1/3 what gravity would be. So that thing's sliding down fast. Now, let's go to orange. I need an orange here. Go ahead and give me an orange out of this. Orange. Okay, so let's go orange mirror. And orange mirror just means kinematics, okay, study of motion. And so let's go with, this is our acceleration. We know our delta x, that's delta x is 3.25. And so I can use second orange mirror, or I'll show you. Second orange mirror is delta x. If you need to go to my website, if you're not in my physics class, if you go to my website where you found this, go back to the website, and it's on my equation sheets. You'll find it like the third equation sheet. You'll see all the orange mirror, blue mirror equations. So delta x equals v naught xt, which v naught is 0, times 1/2 a sub x t squared. All right, and so now I just do my plugging and chugging. I'm trying to find t, so if I solve this for t, that's going to be the square root of 2 delta x over a sub x. And so when I plug all my numbers in, I'll get the square root of 2 times 3.25 meters divided by what? Oh, 3.45 meters per second squared. So You plug all that in, and your time ends up, as it shows in the bottom of the page on the key, 1.37. So T equals 1.37 seconds. Now, if you can't, if you don't know where my website is, if you'll email me, Askey emac, or Askey, DASKEYEMAC at mac.com, at mac.com. I will send you my website. You can go look at the keys and all that. All right, it's open to anybody. So there you go. That's working this problem. A lot of work, and it will appear in the next test, something along these lines. Now it's time for the spring assembly.